Hello everyone, welcome to another Leetcode video. Today we're looking at the problem coin change. This is a really classic Leetcode problem that everyone should understand and is a great introduction to dynamic programming. So the question reads that we're given an integer array coins representing coins of different denominations, and we're also given an integer amount representing a total amount of money. So what we want to do is we want to find the fewest number of coins that we can use to make up that amount. And if the amount of money cannot be returned by any combination of coins, we're just going to return -1. And we have an infinite number of each coin. So, for example, we're given coins as 1, 2, and 5, and our amount is 11. So you'll see that the way we can make 11 with the fewest number of coins is by using 3 coins. And in this example, that would be 5, 5, and 1. So let's look a little bit closer at an example. So let's look at an example where we have 2, 5, and 6 as our coins, and we want to make the amount 7. So a lot of people, when they first encounter this problem and don't really know dynamic programming, they immediately try with a greedy approach. And what that means is that we see the problem wants us to find the fewest number of coins to make up that amount. So people naturally assume that we should always take the biggest coin that we can. And let's see what that actually looks like. So if we were to take the biggest coin that we can at any time, well, we would take 6 away from 7, right? And now we're left with 1 coin. So we need to make an amount 1. But we see we can't actually do that with any of the coins that we have. So we see we basically have to go back and say, well, we can't take 6 away. So let's maybe take a 5. So we take 5 away. This will give us 2, right? So now we have 2 left. Well, we can make another 2 with that, right? So we can take 2 away and get 0. So here we see we have 2 coins. But let's go back, see if there's a better way. And then we can maybe take 2 away the first time. Okay, so now we take 2 away, so we're left with a 5. And then again, we can take a 5 away, we're left with 0. So again, this is 2 coins. So you'll see that we can't really tell if just taking the big coin will give us a result at all, or even the best result. We really have to try every single combination. And this is where we kind of get into the dynamic programming. So dynamic programming kind of follows a pretty typical pattern that you can kind of always apply to all these problems. So first, you want to start with your brute force, right? We saw that here, we have to try basically every combination because we don't know if we pick a coin, if that's going to be part of our most optimal answer or not. So we have to try every single one. However, we'll see that brute force is not optimal. It's going to be really, really slow. So this is where we can go from brute force to what's called memoization. And this 2 portions right here is what this particular video is going to focus on. In the next video, we'll go through the tabulation approach, which is where we go next. So this is memoization, or top down. And then we have finally kind of the most usually space optimized and most efficient way is our tabulation, also called bottom up, right? So basically, every dynamic programming problem can follow these steps. We'll find the brute force algorithm first, then we can apply memoization to it, and then what we can do is convert it to tabulation if we want to get an even more optimal solution. So what does the brute force algorithm for this look like? So let's think of starting at our main problem. So our main problem is we want to find the minimum number of coins that we can use to make the 7. So how do we actually do this? What steps are we going to take? So we'll see that we have 7 and we have 3 options potentially. We can either take away this first coin, which is -2. This leaves us with 5 left. We could take away -5, which leaves us with 2, or we could take away 6, which leaves us with 1. So what is this tree telling us here? This is kind of a decision tree. So you can see that when we make these choices, right, if we take away 2, take away 5, or take away 6, we're actually left with smaller versions of the same problem. So before, we wanted to find how can we make 7 given these 3 coins. Now we're asking, okay, how do we find 5 with these 3 coins? How do we find 2 with these 3 coins, and how do we find 1 with 3 coins? So we can repeat the steps for all these other subproblems. So we could take away 2, so minus 2, and we get 3. We could take away 5, and we get 0, right? So great, we have an answer. So we see this is 1, 2 steps. So we can record 2 as our minimum, or we could take away 6. Well, can we take away 6? Well, no, because you'll see that 6 is actually greater than our 5. So it doesn't really make sense to actually have a negative sense at any point, or a negative amount we can make. So if we ever see that the coin is greater than the problem that we're solving, we're just not even going to consider that route, right? So we've gone through these options. Then likewise, we go through 3. So the only option we can make here is minus 2 again, and we get to 1. So at this point, we actually can't do anything. You'll see that all of our coins here are greater than this 1. So this is kind of our stopping point. We can't actually make any more decisions. So here we have a 2. Our only option we can make here is subtracting 2. So we again get 0, which is the same count as what we've seen over here. And then again, we have a 1, and we can't do anything here. So this is the end of our recursive tree, right? So you'll see that we have found 2 ways to make it, and they both take 2 coins. So this is the brute force algorithm. So let's look quickly at another example. So say we have 7, and we have the coins 1, 2, and 3. So we'll go through the same steps again. So we're going to go, we can subtract 1, we can subtract 2, or we can subtract 3. So this leaves us with 6, 5, and 4. So we'll do the same thing. Minus 1, minus 2, minus 3. Minus 1 gives us 5, minus 2 gives us 4, and then minus 3 gives us 3. So we'll do the same thing here. Minus 1, minus 1, minus 2, minus 3. So then we'll have 4, we'll have 3, we'll have 2. We'll do the same thing here. So you can see, I'm not going to draw out this entire tree, but you can kind of get the idea, right? So we're going to have 3 here. We're going to have 2 here and 1 here. So this isn't even the full tree, but you can probably see a pattern that's evolving, right? We're actually solving the same problem multiple times. So look at this 4 here. We're solving the problem of 4 here and also 4 here. And remember, this problem is how many ways can we make 4 given these coins? And here is how many times can we make 4 given these coins? So these are actually the exact same problem. Similarly with 3, we have the same problem here, same problem here, same problem here. And we have 2 here, 2 here. So you can see that we're actually repeating tons and tons of work here. And this is where our memoization comes in. So what memoization is that whenever we solve one of these problems, say we're at this 4 and we go down all of its branches, we figure out the minimum, and we know what the answer is. When we come back up here, we're going to say, I've solved this problem for 4 already. I already know what the answer is. So when I get here, there's no reason for me to solve the whole thing again because I already know exactly what it is, right? Similarly for 3, if we solve it here, why solve the whole thing again twice? We already know the answer. So memoization is where we take our intermediate results. So we might have like a hash map, and we'll say, I've solved the answer for 4. Let's say that's 2 coins here. So when we see this problem again, which you'll see that we will in this tree, you can just grab this answer instead of recalculating the entire thing again. So this is the idea behind a memoization. So the time complexity here is going to be O of S times N. And S here stands for our amount, right? So whatever the amount that we're given is, times N, which is our coins. And when would this case happen? What's the worst possible case? So what if we have something like this, and we have the coins, this is our amount, and we have 1, 2, right? Well, you'll see that for every 5, we have to do minus 1, we have to do a 4, we'll do minus 1 again, which is 3, we'll have to do minus 2 again, which is 1. So see that if we have a 1 coin, we actually have to go through every number in our amount and calculate that problem out. And for each one, we would basically go through every coin in our list. So we would go through every value in the range S, and then every coin that we have. So that would be our S times N, which is O of S times N. So let's hop over to the code and see exactly how this would work. this represents our brute force solution. So this does not employ any memoization yet, but after this, we will go through and add to memoization so you can see how it works. So we're going to define our recursive function findmin. And memoization, basically 100% of the time, always uses recursion, and then we add memoization on top. So a good place to start with most dynamic programming problems is with recursion. So we're going to create this function, and our base case here is that if we ever get to a remaining of 0, this means that we found a valid configuration of coins that we can use. So here we're just going to return 0. Then we're going to keep track of our answer, and it starts at float infinity. And this is because we want to keep track of the minimum. So we're going to start with a very high value, and then as we find valid configurations, we're going to update our answer. So we're going to go through all of our coins. And we have this one check that says, if the coin we're looking at is greater than whatever the remaining value we're looking for is, then we don't want to do anything. Because say, for example, our coin is 6, but we're only looking to make 5. It doesn't make any sense to use this coin as part of this configuration, because we know it's going to give us a negative value, which doesn't make sense when we're dealing with coins. So then what we do if we've passed this check is that we're going to update our answer and say, our answer now becomes the minimum of whatever answer we found previously, or 1 plus this recursive function. And this 1 represents we're taking this one coin of this value and we're adding it to a potential answer. And then our recursive call is just whatever our remaining is minus this current coin. So say we are looking at the remaining of 5 and we have a coin of 2. We would say we're using that 2 coin, and then we're going to do 5 minus 2. So we're solving this problem for a remaining value of 3. Then at the end, we're just going to return our answer. So then what we do at the end is we're just going to call this findmin function, and then we do our final line here. And basically what this is saying is that if the answer we get back is ever infinity, we want to return -1. And what this means is that if we get infinity back, it means that we found no valid ways to actually make that configuration of coins, so we just return -1. So I'm going to run this. I won't submit it because this is going to time out, because unfortunately we're not using any memoization. So to add memoization, we want to use typically a hash map or an array to store intermediate values. So what's that actually look like? So we can define a memo dictionary, right? And what this is going to do is we're going to store pre-computed values in here. So what we're going to do is when we get our answer back, we're going to store it in our memo dictionary. So we're going to say memo remaining equals our answer, right? And what this is saying is we've just computed the answer for this question of remaining. So we want to save it and use it again for later. Then what we can do is at the top, when we come into this function, we can say if remaining is in our memo, we just want to return that value. So return memo remaining. So let's run this and make sure that it actually works. And we'll submit and make sure it works. And it does. So you see that we always want to start with brute force when we're dealing with dynamic programming. But once we have that brute force algorithm, it's usually very simple to do an optimization of memoization on top. So hopefully this was helpful. If you like the channel, please like and subscribe. It really helps out. And thank you for watching.